lecture deals with the basics of point pattern analysis, and we'll start with a number of examples, including some classic example data sets, and we'll review some terminology. What exactly are point patterns and some of the jargon that is used in point pattern analysis, which is very different. And then if we have time, we'll cover two descriptive techniques. This is not really modeling yet: centrography and kernel density estimation. And then next week, we'll go into some more formal statistical tests, different types of tests based on distance measures, based on scan statistics, and then we'll end, or at least I would like to end, with a discussion of models for spatial processes, which can then also be estimated and so on. I'd like to start with this example. Who knows what this is? Or who has an idea what this is? Nobody? Nobody ever watches the news? This city doesn't look familiar to you? This river curving through the city? This is Baghdad. These are the locations of IEDs in 2005 in Baghdad. And the question then becomes, is this a random event, or are there some clusters of particular locations where these events are concentrated? And then, if so, is there any rhyme or reason to this, and can we possibly try to explain why it is concentrated in particular areas and not in others, or why the patterns are much thicker in some of these axes and then not in others? That's really what it's all about in point pattern analysis. The way we think about this is that these points are events. These are things that happen. And in the statistical literature, this is referred to as a mapped pattern. And the reason it's called that is it's not a sample. Think about it for a second. These locations, these IEDs, these are not a sample of all the IEDs. These are the ones that happened. The ones that didn't happen, we don't have them. We do not observe. So it's not like sometimes in consumer research where you look at certain stimulants, certain advertisements, and then you see whether people buy the product or they don't buy the product. You have both. Or people vote for one candidate or don't vote for a candidate. You have both. Here you only have one outcome. You don't have the other one. So in some sense, this is sometimes called selection bias, in that you only have half of the picture. The events are mapped, meaning we have the location of the events. We do not have the location of the non-events. Is that a window? High-tech lab. I wouldn't be sitting there if I were you. So we have these points, we have their location, they are things that happen. What are we interested in? And there's two different cases. One has more information than the other. One case is we just have the location, that's it. But then we're interested in finding out, are these locations somehow systematically structured, or are they random? And as we'll see in a lot of the discussions that we'll have, the point of departure is spatial randomness, meaning there is no structure. And what we'll be doing in a lot of these specific tests is rejecting spatial randomness. So we say it's not random, therefore it has a structure. Then of course the question is, what kind of structure and what causes this particular structure? And what kind of structure will be looking for clusters or more regular patterns, and the causal causation is then the actual spatial modeling, spatial point cross modeling. That's one situation. The second situation is when we have more information, where we have both the location as well as some magnitude associated with that location. And the classic examples, as we'll see in a few minutes, are tree patterns, where you have both the location of the tree and the size of the trunk of the tree. So then you're interested in modeling not only where these trees are, but also how big they are. And are larger trees together, or are larger trees surrounded by smaller trees, and those kinds of patterns. And so this kind of situation is called a marked point pattern. So you have a regular point pattern, which is just a location, and then when you refer to it as a marked point pattern, then you have a value associated with that location. And even though we will focus primarily, at least in this course, on the pattern and assessing whether there is some systematic structure in the pattern, what we really want to know is what is the process that causes this pattern. And this gets us back to this problem that I discussed the other day, the identification process. Namely, or the inverse problem, as it's sometimes called. Namely, that a particular pattern can be realized by different processes. And oftentimes we do not have sufficient information by just observing the pattern to be able to tell which of the processes yields that pattern. And we'll see that hopefully in a couple of weeks. We'll do some simulations of different patterns, and you'll see that the outcome, the dots on your map or on your plot, look exactly the same, but they're two different patterns, two different processes that are yielding these points. How do we conceptualize this? So we think of these locations, and in the classic point pattern analysis, this goes back to the 60s and the 70s, points were conceptualized as somehow floating in a space, points on a plane. And this is an isotropic plane. Now, isotropic, who knows what that means? What does iso mean?
Pick one.
Same. So isotropic means that the plane is the same everywhere in all respects. Pancake, flat. Direction doesn't matter. Absolute location doesn't matter. If you take a piece of the plane and you move it over to another position, nothing changes. It is a complete state of equilibrium, if you wish, where the only thing that matters is relative positioning in the form of distance. So we simplify the problem. We take out all structure except distance. And distance will be the means through which we assess whether or not these patterns are random or structured in some particular fashion. Isotropic plane means that there is no effect of translation, meaning moving the points around or moving a subset of the data around. The information that you get does not depend on the absolute location. So in some sense, if you think you can observe a huge plane of forest of trees, whether you take all those forests or some particular subset of the trees, you have the same amount of information about the process, because it doesn't change. Isotropic is a very strict requirement because it also precludes directional effects. Now, directional effects, as we'll see, are actually fairly common, and so there's two gradations. One is when you don't allow any effect of translation. The other one is you also don't allow any directional effects. When you impose these two constraints, then what you're left with is only distance. And that's the easiest way to deal with problems. And as I mentioned, the classic examples come from ecology. They deal with tree seedlings, rocks, stuff like that, birds' nests, different types of objects that are located in space. And the distance in this isotropic plane is straight line distance only. I'll be using an example throughout, which is actually a real example of criminological data dealing with homicide locations in Buffalo, New York in the 90s. It's a 10-year period. And what I wanted to show you is how one actually gets that, and also some problems. We talked the first lecture about geocoding, and so the point of departure here too is geocoding. So you start with a record of case numbers and addresses where all these homicides happened. And then those get translated and turned into latitude, longitude coordinates. Now, as it happens, case 9014 has an address, but it doesn't have an address that can be geocoded. There's no number in there. And if you just kind of click the button and let the geocoder work, you get weird results. I know that because I got them last Sunday. You get 0, 0 as the coordinates. And you just move this into a shapefile and make the map, and ArcGIS doesn't protest because it just ignores them. But they're there. And then if you try to do certain manipulations, as we'll see later, everything blows up. So this process, let me just reiterate it. I remember I mentioned it the first lecture as well. Geocoding is very nice, but it's almost never perfect. And so you lose some information. This is important if there is a systematic connection between the information that you lose and the geocoding and the spatial location where they are. So if somehow systematically in one part of the city you would have very poor locational information, and that part of the city is somehow different from the rest, then that would introduce a systematic bias in your analysis. So this is something else to think about. So assuming everything goes well, we start with these addresses, and then we end up with this. As I like to say, points floating in space. These are the homicides in Buffalo over a 10-year period. Now this is what classical point pattern analysis uses as the framework. And it likes to take these points floating in space and somehow assess whether there's any systematic structure in this or whether this is just random. And of course, when we're interested in understanding what is going on, we like to put these points in context. And one example of a context is to add the city boundaries to it, and the water of the lake and the river, and the census tracts, and you could add street patterns and so on. And then all of a sudden things start looking very differently. So if you go back to the previous slide, you see these kind of points with some blobs here and there that might suggest some clusters. If you put the city boundaries around them, all of a sudden you start seeing some maybe systematic patterning in certain parts of the city. And you also see that a lot of this white space is white space because there isn't anything there. It's outside of the city or it's in the water. And now, when we're interested in understanding and describing point patterns, we don't want to model them where they can't be. We don't want to put homicides in the lake. Or if we study homicides in Buffalo, we don't want to put them outside Buffalo. So these are the kinds of issues that create some tension between the classical approach, which came out of ecology, where this assumption of a uniform plane is fairly acceptable, to situations in socioeconomic analysis where that's not acceptable. And we'll see later on some other aspects of this that we need to take into account. An important characteristic of point patterns is what we refer to as intensity. And intensity is like an average, is what is called a first moment of a distribution. Moments being characteristic of a distribution. So the first moment has to do with central tendency, Second moment has to do with spread around that. Third moment has to do with symmetry and asymmetry and so on. So how do we characterize a point pattern as the central tendency of a point pattern? And one way to do this is to just figure out what is the average number of events per areal unit. What is the average number of homicides per square kilometer? That happens to be the unit of this data set. So this characteristic is called the intensity of the point process. And we often use the symbol lambda for this. And it's simply the ratio of the number of points divided by the area of the study. Okay. Now in our Buffalo example, what is the area of the study? Let me go to the extreme. What is the area of the study? We don't have clear bounds. Think about this for a second. Now, why does this matter? Well, it matters because you're computing a characteristic of the pattern by dividing the number of points. That doesn't change by the area. So if you take your area as all of this white space on the slide versus the city boundary or versus something else, it's going to make a difference. And let's see what kind of difference it makes. So what we try to do is have some reasonable boundaries for these points. I mean, we could say, well, the slide is the slide, that's the space we use, that's the density we compute, that's the intensity of the pattern. In practice, one often uses some kind of bounding box, a bounding rectangle, which includes all the points, but has a regular shape, a square or a rectangle. Or you could use city boundaries, and then later on we'll see another approach, which is a convex hull, which is also often used. So let's look at this bounding box. That is the rectangle formed by the most extreme coordinates. So we take the smallest x, which is these points here, they're the leftmost points, and the lowest y, which is the lowest points, that corresponds to these points. So the combination of this x coordinate and this y coordinate is the lower left corner. And then the reverse, we take the highest x value, y value, and the highest x value, and that makes the upper right corner right there. So the rectangle that connects these points is referred to as a bounding box or a bounding rectangle. And so now we can compute intensity of the pattern by taking the number of points and dividing them by the area of this rectangle. In this particular example, it's geocoded and projected so that they're kilometers. So we can come up with a number that says average number of homicides per square kilometer. And that's a measure of the intensity of the process, and you can compare this year by year and see if it goes up or if it goes down. We could also take the city boundary, and then in a few minutes we'll compare the area of these two. And what we see here is that this is more realistic, but there's also a bunch of white space, and we already know from the map we saw before that all of this is really artificial. This is a legal boundary, but it's actually in the water, so there's nothing there, or nothing can happen. The favorite notion in the literature is to use not this arbitrary bounding box or some arbitrary city boundary, but to use a concept of the tightest fit around the points. And that is a concept of a convex hull. You can think of these points as being spikes, and you take a big rubber band and you fit it around all the points. The tightest fit is the convex hull. This is a complicated mathematical problem in computational geometry to actually compute the convex hull for a number of points, but there are several solutions. It's fairly well known. It's kind of a classic in computational geometry. Now, for the spatial point patterns, a question arises when you use this convex hull, because the tightest fit means that several points will be on the boundary of the polygon. And for a number of reasons, that may not be such a good idea, because later on, we'll be using distances to other points and measures like that. And when you have too many points on the boundary, you have what we call boundary effects. It's like in time series, where you have a starting point problem. There is a t0. After t0, you can look at the next day and the next day, but there's always some point where you start. Here it's the same, but in 2 dimensions. In that if you have too many points on the boundary, that creates complications for the various statistics, distance measures, and things like that. So there is a result, it's a fairly old result, to rescale this convex hull to better approximate the spatial domain of the points. Essentially, it moves, for all practical purposes, moves the rubber band out, if you wish, a little bit away from the vertices of the original convex hull. And this is really useful for very small samples of data. For larger samples of data, it doesn't make a big difference at all, because the adjustment pattern, and I'll spare you the math, is 1 over the square root of 1 minus m over n, where m is the number of vertices of the convex hull. In our Buffalo case, the convex hull has 17 vertices, but there's something like 569 points. So this adjustment is marginal. It's like 1.01. It doesn't make any difference at all. In fact, if you look at it, I just wanted to show you the difference between the two. This is a straight convex hull, and it's drawn in ArcGIS. And then this is the adjusted convex hull, and unfortunately it's not very sharp on your screen, but this is drawn in R. And if you look very carefully, say up here, see this little point, there is a little space between the line and the point. Whereas if you go to the previous slide, there is no space. Those points on the convex hull are exactly on the polygon. Okay. So the adjusted convex hull creates a little buffer space around these extreme points. If you look very carefully, maybe if you look at it on your own screen, you can see that around this corner here, there's a little bit of space, and it stretches the convex hull away. This is something you should know about, but with large data sets, it really doesn't make a lot of difference. This gives you an idea of the different shapes applied to the same point pattern. So this is the same Buffalo point pattern with the original city boundary, this red shape here, then the convex hull, which is a lot tighter inside, and then the rectangular bounding points. And for each of these, we can compute the intensity, which, remember, is sort of a mean, an average number of events per unit of area. And the unit of area in this particular case is a square kilometer. We have 569 homicides. Depending on the boundary that we use, we get a range, not a big range, from about 121 square kilometers to 91 square kilometers. The tightest is the convex hull. So as a result, that will have the highest intensity, on average, 6 homicides per square kilometer. So what this means is that if this pattern is stable and in equilibrium and is spatially random, then no matter where you plop a square kilometer in the city, on average, you should have about 6 homicides in the 10-year period. 6 homicides per square kilometer in a 10-year period. That's a lot of homicides. And when you look at the map, there's parts of Buffalo where there are no homicides at all. So what this suggests is that maybe this intensity, which assumes uniformity throughout, is not a good approximation of what really goes on. And we'll see later on today, we will relax this requirement that the intensity is uniform and allow it to vary by location. And you see then with the bounding box, which is the biggest area, 121 square kilometers, we get 4.7. So the difference between 4.7 and 6.3 is not that big, but it shows you that it does matter. And especially if you want to draw policy conclusions, you know, it's like lying with statistics. You know, these are all correct. None of these is wrong. But what you're doing is manipulating the denominator while the numerator stays fixed. And I didn't even want to bother computing the area of the complete slide where those points were floating, because that would be much, much lower. So important thing to remember, intensity is a summary of the process. It's like an average. And intensity that you compute will depend on the area of the points that you study. And you need to come up with some criterion to define that area. Now, if you study birds' nests on an island, you're all set. Your area is the island. Right? But if you study homicides in the city, it's not that straightforward. And maybe some of the geometric suggestions, like a bounding box or a convex hull, might not be that appropriate for your particular study. Because these points floating in space are missing an important aspect of the process. The point of departure, the first slide I showed you, was a list of addresses. These are points on a network, a street network. So if we look at them on a network, it's much more realistic. And we avoid putting homicides in the lake. We avoid putting things in locations where they can't happen. But as a result of that, we don't use straight line distance anymore. And we have to compute the distance as a shortest path on a network, or as an approximation, we can use Manhattan block distance if the city uses a grid system. Or we could use economic distances, travel times, travel cost. If, say, if there's congestion or there's tolls, then you can take all that stuff into account. So you can get a much more realistic view of the location of the events and of the distances involved in computing different statistics for the events. Now, the difference is illustrated with this slide. This is, again, a real pattern of the, I mean, you guys probably don't remember this, but in the early 90s, there were severe riots in Los Angeles, where people basically got pulled out of their cars and beaten up and things like that. This is the location of incidents during these riots, floating in space. This is the location of these same incidents, but put on the street network of Los Angeles. And so between the two of them, this gives you much more information on specific locations where there may be hotspots, like along a particular street or at particular intersections in the street network, which the previous slide does not give you. So we'll talk a little bit about point pattern analysis on a street network. The bottom line is that basically you use the same techniques as point patterns in space, except that your distance measure is different. And so instead of using straight line distance in an isotropic plane, where direction doesn't matter, you have to compute network distances, which is an additional complication. But other than that, the conceptual basis for the statistics, for the tests, for the models is the same. The only difference is that your potential set of potential locations is constrained. And the same principle goes if you want to put other types of constraints on your data set, like mask, what we call masks. For example, if there was a big lake in the middle of the city, you don't want to consider a point pattern that could put events in the lake, unless you're studying fish. But you want to take that out. So that then, again, complicates your analysis, is that in that whenever you do, say, a randomization where you randomly put points in space, you have to make sure that they don't land in the lake. And it's a similar rationale in point pattern analysis on the street network or on any network. We'll refer to it a little bit, but we won't get into a lot of the technical details. What I want to do now is just give you some examples of specific design. So far we've talked about point patterns in kind of a generic sense. But what I want to do now is to illustrate and show you some specific settings that have statistical repercussions. One thing that I haven't talked about is we just looked at these points and they just happen, which assumes a homogeneous background. But say if you're interested in looking at disease and you're looking, say, at cancers, thinking of this as happening in a uniform background doesn't really make a lot of sense. It only makes sense in one particular setting. What is that? So you're looking at sick people coming out of a population of people. If that population is uniform, then we're fine. Then our points are what they are. If the population is not uniform, then where would we tend to have more sick people? No. No hospitals. Addresses of sick people. Where would they meet? If the population is distributed unequally, with lots of people in certain places and few people in other places, everything else being the same, where would there be more sick people? Where there are more people. Yeah. So we need to control for this background distribution. And that design is called a case control design. So what you want to do is to have 2 point patterns. One, say, for the people with the disease, and then the other for everybody. And what you want to see is whether the pattern for the diseased people, for the sick people, is in some way different from the pattern of the population. Once you admit or assume that the population is not uniformly distributed, you have to account for that heterogeneity. It's the same if you look at car thefts. We looked at that little map from the paper in the first lecture. Where will there be more car thefts? Where there are more cars parked in the street. Does that mean it's a cluster? No. It has to do with the difference in the background population. So that has to be taken into account if you try to model structured patterns in the data. So this is referred to as a case control design. This comes out of the medical literature where you have, the placebo thing. You have medicine and then half of the people get the medicine and the other people get something that looks like medicine but it doesn't do anything, and then you want to see if there's any difference between the two. It's the same idea. We have the one pattern for the event of interest, say particular kind of cancers, the other pattern to reflect the background population. Now, in some cases, particularly in the medical literature, this doesn't have to be the actual population, but it could be, say, another cancer. And you see this a lot in public health studies, that the one pattern is, say, a specific cancer that you're interested in, and then the other pattern, the background, which is supposed to reflect the heterogeneity of the population, is some fairly common cancer. And then you look at the two different ones. Now you can get out of this case control setting and also think of, say, different points in time. So you look at one period in time, which you say is the control, and then another period in time is the case, and you're interested in finding out whether these patterns are constant over time or change. And what we're interested in this case control design setting is the concept of relative risk. So we want to find out if somehow the pattern or the density of the cases relative to the density of controls is different. Are there spikes, for example? This is a classic example from the textbooks of Lancashire in England, where we have the red dots are the cancers and the blue dots are the population of interest. And there is a, it doesn't show here, but there is an incinerator around here. So something that burns trash or something. So the interest is there a heightened concentration of these particular cancers, the red dots, around this incinerator or not? This is a very common problem, a cluster problem. Is there a cluster of leukemia? Is there a cluster of a particular kind of weird cancer? In Long Island, there has been a long ongoing debate whether or not there is a cluster of breast cancer in Long Island, and so on. And in each of these cases, it's a similar problem to this. You can think of many different instances. Think of red as something of interest and blue as the background population. And what we're interested in is whether this red pattern is somehow significantly different from the blue pattern. Whether the concentration of the reds is much higher than the concentration of the blues, which would suggest a heightened relative risk for a spike in the distribution. So that's the case control design. Another classic case, which we already alluded to, is marked point patterns. And marked point patterns are situations, as I mentioned earlier, where you have both location and value. So we're interested not only in finding patterns in the location, but also in finding association between location and value. And the classic examples are trees. This is, a lot of textbooks use this data set. It's called the longleaf pines data set. It's a particular forestry study where these trees are plotted as circles, and the diameter of the circle shows the size of the tree. So the bigger circles are bigger trees. And then we're interested in finding out, do big trees hang out together, or are big trees surrounded by small trees, or any other such combinations of patterns. And with a little bit of imagination, you can think of other such patterns that are not trees. For example, in the IEDs, you could think of how many people are killed. Or if you do, you look at, sales events that happen in space, say drug deals, you could look at the amount that was transacted in these drug deals. And you could find, for example, that high amount transactions happen in different locations than small amount transactions. That small amount transactions tend to be clustered in particular locations, but high amount transactions are not. And so with a little bit of imagination, you can think of a lot of different contexts where you have this marked point pattern, where you have the additional information, which is also, of course, additional complication, that you have both value and location at these points. And then the last one is the so-called multi-type patterns, is where we have categorical data with more than one category. And again, the example here is a tree example where you have a test plot with different species of trees, like in an arboretum, for example. And then you're interested, again, category by category, you can look at the pattern in a univariate sense, or you can look at it in a multivariate sense, where you're interested in finding out, and this is almost impossible to see on the screen, but if you look at the handout, you may be able to see. This is also a classic data set. It's a Lansing Woods test plot. And there are 6 species of trees plotted with little triangles, squares, and circles and things like that. And the focus then is there any patterning between these species? Do certain species locate nearer each other or further apart from each other? What is the association, not just one at a time, but across categories, which is more complicated. And before taking a break, let me make a connection between the counts, the events as occurring in space, and then in a sense their counterpart is when you add up the events in a container, as I like to say. And it's the same thing in time series analysis. You can, for example, classic situation is light bulbs when they pop. And you can keep track of when the light bulbs pop, and 1 month goes by, one pops. Another month, another one pops. Or you can group them and you say, how many popped in January? How many popped in February? Same here. We can look at where these points are located, where did these homicides happen, or we can say, how many homicides happened in this census tract? How many homicides happened in that census tract? So there's a direct connection, and we'll see this later in a little more sophisticated way through the mathematics of the distributions, that there is a connection between these events and their aggregates, which are counts of events. And the aggregates then are used to compute probabilities that events can happen. It's another way of getting at that question by estimating a risk. And a risk is essentially the probability of an event, which we estimate by counting the number of events per area, which is a rate. So the study of rates and risk is very tightly connected to the study of the point patterns of the events. There's basically 2 different ways of looking at the same processes. And to illustrate this, let's look at our Buffalo data again, and at 3 different representations. The blue dots are the positions of the effect of the events, and then the shading is an extensive variable, a simple count of homicides. Now, as I mentioned a few minutes ago, as such, that is not that interesting, because if there are more people, there could be more homicides. So this by itself is not useful information. What we really need to see is how do these events compare to the population at risk, which is given in this shading. So this is the spatial distribution of the points in blue, and then of the population of the census tract behind as the background. And let me just point your attention, obviously, in here, there are some concentrations of dots in the center of the city that have a lighter background, fewer people. Right? Here is another one with a few homicides but very few people. Now if we put this together and we compute a rate, so the number of homicides per population, then we get this. And see how this one here pops out. Why? Not because it has so many homicides, but there's basically nobody there. So you take a ratio of, say, a similar number of homicides as in other parts of the city, but because there are so fewer people, the rate is elevated. So this then is a spatial distribution of the homicide rate by census tract put against the point pattern of the events. And these are 2 ways in which we're going to approach modeling and understanding the probability that events happen, which is really what we're interested in the end. One approach is the one we'll take these few weeks, is focusing on the point patterns. Another approach, which we'll mention in passing as a special application of spatial regression, is to focus on the rates and the counts in the census tracts. So this gives you kind of an overview of some of the basic concepts, the basic types of point patterns, and one characteristic